Hello, physical scientists. We are doing activity 6 that's wrapping up our unit called What Are Our Choices for Supplying Energy for the Future? In our class, it's also known as Lab 5.2. We're going to start this energy efficiency activity by talking about the grid. The grid is the electrical grid. So you can see the maps of the grids all over the country that shows how the United States and Canada and Mexico cooperate with each other to distribute electricity all over the country. So if for some reason an electricity generating plant here in St. Paul goes down, we can get electricity from other places. They'll share with us until we can get our plant back up. And so there's no disruption in the electrical grid. However, we saw last year when there was a big snowstorm in Texas, Texas is not part of the rest of the electrical grid in the United States. It's its own system. So if there's a problem in Texas, Texas has to solve its own problem. Unless you live in Hawaii or you live off the grid, meaning you make your own electricity from solar panels or wind or however you get it, you get electricity from a variety of places. The image shows the electrical grid in the United States. It connects to Canada and Mexico, allowing electricity to flow quickly where it's needed, when it's needed. As energy demands change both daily and seasonally, electricity flow across the grid allows electricity to flow almost instantly from areas with more capacity to areas with more demand. So, for example, say it's a nice, fairly cool May day here. People don't need air conditioning and they don't need much heat. It's one of those perfect days in Minnesota. But maybe Arizona is already, or California is already hot. We can send some power over to California, or even just down to Iowa, where they might need AC. Electricity demands change throughout the day and across seasons. Give some reasons for increased demands during the day and across seasons. Well, I can think of a couple things. Air conditioning is a big deal. It takes a lot of electricity to run an air conditioner. So if you are going to, on a really hot day, there's a big demand on the grid. Another thing is heating. Some people use direct electric heat, but a lot of people have electricity somehow connected to their natural gas heat. For example, in my house, we have radiators, so we have a pump that runs on electricity to pump that hot water around our house. The natural gas heats it, but the electrical pump sends it around the house. Same with your furnace. If you have forced air, you have a blower that's blowing that hot air around the house, so your furnace isn't really going to work well without electricity. So summer and winter are big demands for electrical energy. Also, think about during the day when you use the most electricity. What do you do when you get up? Your alarm goes off. That's plugged in. That requires electricity. Maybe you go to the bathroom and turn on the light. That's electricity. Maybe use a bathroom fan. That's electricity. Maybe use a hairdryer or curling iron. That's electricity. Maybe you put some toast in the toaster. That's electricity. So mornings are a big time when everybody's kind of bustling around the house, trying to get out, get ready. Also, when people come home at around 5 or 6, they start dinner. Maybe you have an electric cooktop. They turn on some lights, especially in the winter. We need more lighting in the winter because it gets dark earlier. Some things you might do when you come home too is maybe throw in a load of laundry when you get home. And so all those demands, the demand for throughout the day tends to be, they call it the camel. There's one hump at the beginning of the day and there's another big hump of electrical use at the end of the day. So electrical losses. We can make a lot of electricity, but when we send it around, we lose some of that electricity. This graph shows how some of this electricity, about this 0.94 divided by 15.8, equals about 6% is what's called line loss. That means some of the electricity gets lost along the way from where it's generated to where it's used. So give me a St. Paul example. Some of our power here in St. Paul comes from a big wind farm about 3 hours south of here. In order to get that power up to St. Paul, they have to put it in a high voltage line and really push it hard to get it here. On its way, some of that electricity turns into heat, is transformed into heat energy, and then isn't useful for isn't available for us to use when we plug in our lights. So that line loss, or losing some electricity on the way, makes for some inefficiencies in the electrical grid. One of the ways to get around that is generate your own power. Over my head here, about 4 feet from my head, literally, there are solar panels, and we're generating electricity right on site. So there's almost no line loss when you generate electricity very locally. Energy conversions are not very efficient, so we lose energy, say, when we go from heat energy to creating steam to spinning a turbine. That's got some inefficiency built in there. There are losses, there are line losses as you push electricity through long distance lines. Some new thermal power plants, those that heat water to generate electricity, including fossil fuels and nuclear power plants, are combined heat and power plants. These power plants capture some of the waste heat to generate more electricity, so they kind of recycle their own heat. The diagram shows electricity flow in 2018. The left side shows the sources used in electricity generation, and the right side shows the end uses for generated electricity. So here's the left side, here's how we're generating it, and here's how we're using it. Note the difference between the amount of usable electricity on the right side and versus the amount of energy being contained in the generating sources on the left side. So total energy from all the generating sources is 38.83, and that's in BTUs. When it gets out for end use, it's only 15.18. So we lose a ton of energy here when we convert it between like heat and electricity. There's a lot of inefficiency there. So it goes from 38 down to 15. That's pretty bad. Considering the information in the electricity flow diagram, which change in electricity generation and delivery would most increase the efficiency, reduce the losses of electricity delivery? Well, if you're going to focus on delivery, not just generation, delivery, if you produce electricity closer to the use site, like your house, then you lose less when you deliver it. So if you want to solve the delivery problem, that's producing it closer to your house. If you want to solve a problem with efficiency in converting the fuel to heat and that heat to electricity by producing steam and spinning a turbine, then your best bet is to upgrade your power plants. It looks like here that nuclear is a little bit better, a little bit more efficient, but I don't know. I can't really get that from the diagram here. So if you want to worry about delivery, the best thing to do is make it right at your house. I'm making electricity about 4 feet from my head right now. Not going to have any line loss. And I don't need to convert that electricity. The sun shines, I get electricity straight out. I convert light energy straight to electricity. There's no converting it to heat and then spinning a turbine. I don't need to do that. Solar panels are pretty efficient at going straight to the source. Although the sun's not shining today, so we're not making that much power. That's the problem with solar panels. You need a bunch of sources of electricity all combined to make up for the fact that the sun doesn't shine all the time. You can pick your certainty. I calculated line loss. I took 0.94 over 15.18 as about 6% of the electricity coming to the end users. So we lose about 6% in line loss. And that's just one of the inefficiencies in the system. A lot of it is conversion of fuel to heat, burning the fuel, getting that heat converted to steam, that steam spinning a turbine, that turbine being efficient in making electricity. There's a lot of issues there. So let's look at this graph here. How is electricity used in commercial buildings? Now, a commercial building is something like you could think of a big box store, or maybe you've got a mom and pop shop down the road. Anything that's a business that's open for people to come in and buy things, that's a commercial use. So if you have a Home Depot or Target or a Cub Foods, a super big supermarket, Walmart, those are commercial buildings. And the biggest use in commercial buildings, look at that big red quarter of the pie graph here. That's space heating. So the highest demand for electricity here is space heating. What percentage is used for lighting? Well, that's the yellow chunk, and I'll let you figure out what percentage that is. Food service buildings and hospitals are the most intensive users of energy. You can see if we look at this graph, food service and inpatient healthcare, aka hospitals, are using the most energy. And food service hasn't really cut back much. Most of these uses, you can see the yellow is a little bit bigger than the blue. They're finding ways to cut their electricity, but food service has not. And so maybe that's a great place for all of us to think about efficiency. Most buildings actually use less energy in 2012 than they did in 2003. One of the things that businesses have done is they put in different light bulbs. So an incandescent light bulb has a wire in the middle of it. You've probably seen one. This is an LED bulb. It's got kind of a big crystal down in there, and there's a light emitting diode in there. It uses much less energy than a regular light bulb, and it's brighter. This is a compact fluorescent. It also uses much less energy, but there's one drawback to these. They have mercury in them, and you have to recycle them in a special facility. So better lighting can save a lot of energy. Refrigeration efficiency. If you've gone to a grocery store lately, more and more of the refrigerated items you have to open a door to get. And that's because they don't want to run. Like if you've seen where they have like the cheese and the butter, usually kind of the dairy section, or maybe where they have the tortillas. That's an open refrigerator, and it's like running your refrigerator with the door open, which wastes a ton of electricity. So putting doors or flaps on those freezers and refrigerators that used to be open saves businesses a lot of money. Also, controlling the entrances and exits of your buildings. If you've gone into a big commercial building and kind of gone in two different doors, one, maybe they have some shopping carts, and then you have to go in another door to actually get in the store. That helps control the temperature in the building by not letting as much warm air go straight out the door. So if we look at where a typical energy, how much a typical family pays for energy in a year, A big one here in Minnesota and all over the country is heating. The biggest chunk of this pie is heating. Things you can do to reduce the heat bill. You can insulate, you can put in weather stripping. We'll look at a video later that can give you some ideas about what you can do to save energy on heating and cooling. You can watch this video, and I highly recommend you do. It kind of walks you through your house and discusses the things that you can do in each room to improve the energy efficiency of your house. Buying new appliances isn't an option for everyone, but if you do have to buy a new appliance, looking for Energy Star rating is always a good idea. So question 11, watch the video. Question 12, if we are all reducing the amount of energy that we use, that means the electrical grid doesn't have to deliver as much energy, and we don't need as many power plants. If we don't have to build power plants and burn fossil fuels, that saves carbon dioxide being put into the atmosphere. So if everybody does a little bit to conserve energy, maybe gets 1 or 2 new light bulbs for the lights you use most often, that little bit for everybody will add up to a lot of CO2 not being put in the atmosphere because that coal isn't being burned or that natural gas isn't being burned to generate electricity. So conservation, generating megawatts. A megawatt is electricity that you don't have to use. It's like it's negative energy that you've saved. We've learned a little bit about how electricity is generated and some of the environmental impacts of different generating sources. As you may recall, electricity production is measured in megawatts. Although you're unlikely to generate commercial amounts of electricity, you can generate negawatts. A negawatt is a term used to denote megawatts that were not used. So negawatts are the amount of energy we save. If megawatts aren't used, they don't have to be generated. And we don't have to build extra power plants that burn more fossil fuels. Essentially, you can generate negawatts through energy conservation. Conservation includes reducing energy use as well as using energy more efficiently. When less energy is needed, the environmental effects of extracting resources to generate electricity are lessened. The Energy Star program, run through the Environmental Protection Agency, rates energy uses appliances for their efficiency. To earn the Energy Star designation, a product must be at least 30% more efficient than other similarly priced products in the same category. When we shopped for a dishwasher and a refrigerator, we looked for, because our other dishwasher and refrigerator had died, so we had to get a new one, we looked for Energy Star appliances, and as a result, we use a lot of less electricity than our neighbors. One thing you can do to save energy in your house is make sure everything is insulated. On the bottoms of doors, you can put weather stripping. That was in the video on the previous page. And here are some ideas about how a business might generate negawatts. You can come up with more ideas. If your parents have a business or you know someone with a business, you could ask them for more ideas. The less electricity that we need, the fewer power plants we need to have, the less fossil fuels we burn, and that makes less CO2, which accelerates climate change. So if you use less electricity and everybody else does the same, we'll cut down on the amount of greenhouse gases we put out. So we have to, as a a nation and as a world community have to think about what kinds of electricity needs are going to be coming up. Because if there's electricity that we need, we can't just build a power plant overnight. We have to do some planning. Will we have enough energy to meet the demand for electricity? In the short run, yes. But in the long run, the questions are more open-ended. The demand for electricity and energy in general is increasing. More people around the world will have access to electricity, and people will have more electronic devices that will require electricity. Think about all the things that you plug in to your power strip. Maybe you have a phone charger, maybe you have lights, maybe you have your alarm clock, your computer charger. All that stuff requires electricity, and so the more things we plug in, the more power your house needs or your apartment. The Energy Information Administration, the Independent Statistics and Analysis Branch of the U.S. Department of Energy, forecasts the short-term outlook for energy consumption, generation, and prices. So this was written in 2018, so these predictions were made before they had data from 2020 and 2021. So if we look here, we can see that the forecast for 2020 and 2021 looks like it's going to go down in 2020 and go back up in 2021 just a little bit. Same thing on this components of change. It looks like commercial and transportation sales are going to make some of the demand coming back up. So 2020 looks like it's going to go down a little bit, but 2021 it's going to go up, and I would bet as more and more people buy gaming systems and phones and computers and laptops and TVs are a really big energy sucking device. And the bigger your TV, generally the more power it uses. So big TVs are awesome, but they also use a lot of electricity. What would happen to the fuel mix for electricity generation in 2020 and beyond? So let's look at the fuel mix here. It looks like for 2020 and 2021, renewables are going to come up a little bit. It looks like coal might have to come up a little bit as natural gas goes down a little bit. It looks like the total mix, though, we're definitely going to see some strength in more renewables. Let's look at these graphs. If we drew a line through the trend here and the forecast, you'd probably see a slight upward trend. And we see that as well in the bar graph, 2020 and 2021. We're seeing a lot of forecast increase for the amount of electricity needed. So this is the price that's going up a little bit, and this is a bar graph of kind of the similar information. This is the increases in prices. And so you pick your certainty rating, and you can talk about the information on the graph here and here to explain your certainty rating. And when you're done here, you want to hit show all answers. And then you want to copy and paste all these answers, put it in a document with activity 3, 4, and 5. And when you have 3, 4, 5, and 6 all copy and pasted into the same document in Notability or Google Docs or Word, you can hand in that whole thing. Make sure you highlight your answers so I can grade it really easily, and hand that in to Lab 5.2. Thank you very much. I look forward to grading your work.